Good afternoon, everyone. I think we should get started. Okay, so today we're gonna spend 15 to 20 minutes to walk through a few important concepts for our class. So basically, some knowledge review, but that does not mean a comprehensive review of all what you have learned from like linear algebra, statistics, probabilities. This is just a jump start because those concepts are so fundamental. Without them, we cannot start with our machine learning models and algorithms. But when you are still unsure or cannot memorize, say how to compute conditional probability densities, how to test conditional independence, please do sit down, open your textbook, pick up details. Hopefully, this will just give you a guide to look at the knowledge you have learned from first year, second year on grad study. Okay, so first we start with the definition of random events and probabilities. Right? So we know that our world is filled with uncertainty. So we need mathematical tools to characterize the reason under uncertainty, right? Those are about statistics and probability theory. They're starting with the definition of random events, right? So in math language, we use sets to represent random events. Right? And each element in the sets is some atomic outcome from some random experiments. Right? For a concrete example, suppose we toss a coin for 5 times, right? So we want to look at the results of 5 tosses, right? That are the events that we're interested in. Then we can use a set of 5 elements to represent a specific event. Right? So you can say each element is either head or tail, the outcome of 1 toss. So this is atomic, right? This is atomic. So obviously, even A indicates that the first 12 are heads and the remaining 2 are tails, right? So obviously we have other possible events as well, which can showing that your first toss ends up with tail and then head, tail, right? So you have many possible events, namely the outcomes of your random experiments. Right? So this is the definition of the. This is how we represent random events using sets. Right? So given some particular event, right, we assign a probability to measure the chance that event happen. Right? Remember, those events are random. Right? They have some chance to happen. They have some chance not to happen. Right? So we use a number which is between 0 and 1, which we call probability, to measure the chance it happens not, right? P of A and P of B. And we use set operations to create new events based upon the existing events, right? So suppose I have 2 events A and B, right? Then if I want to represent a new event that both A and B happen, we use an intersection operation, right? So the intersection of A and B represent even that both even A and B happen. Right? Another event could be like A or B happens. So those 2 types of events are totally different. So be aware of the subtle difference, right? So A or B happens might have the cases that A happens, but B does not happen. Or A does not happen, but B happens. Or A and B both happen. Now how can we represent this event? Right? A or B happens. We use the union operation. Right? So the union of A and B represent event that A or B happens. So you can say, by combining a bunch of events using the set operations, we can create many new events. Right? It can be very complicated. So it'll be interesting to see that when we do this even combination through set operations, how can we compute their probability, right? So here's the basic rule to compute the probability of A or B happens, namely P of A union B, right? So it is equal to the probability of A, P of A plus probability of B happens, subtracted by the probability A and B both happen. Right? So we have a general version of this formula. So I'm pretty much sure this general formula appears in every statistical book. Right? So suppose we have like n events, arbitrary finite number of events, A1, A2, A3, say An, right? So how can we compute the probability that A1 happen or A2 happen until An happen, right? That's the probability of union of all A1, A2 to An, right? So it's a long formula, but it's very has a strong regular patterns, right? You're adding the probability of each individual event happens subtracted by the probability that the intersection of pairwise events, then add again the probability of 3 triple events happen and subtracted by 4 events happen, and add and subtract until the very end, right? So yeah, if you still have some impression, just take a look at your old textbook. So those are about random events and probability. And next, the fundamental concept is called random variables. So what is random variable? If we use numbers to represent the outcomes of random experiments, then we call this kind of number as random variables. That means if you associate the number with some random experiments, then this number has some randomness. So we call random variables, right? So why would we like to introduce random variables? Because we want to investigate some common properties of all kinds of random experiments, right? So some random experiments might be, the outcome might be some coins, heads or tails, right? Some might be the weather, right? The other might be like stock prices, right? We do not know, right? But if we want to look at their common properties, we need some more abstractive representation. That's why the random variables are proposed. The concept of random variables are proposed, right? If we use random variables to represent the experimental outcomes, then the events can be represented by random variables falling in some regions, right? So if you have real value random variables, then some events can be represented by the value of the random variables that falls in some particular interval. Let's use the coin tossing as the example again, right? So when you toss a coin, the outcome will be either head or the tails, right? So correspondingly, we can introduce the random variable x, which is binary. So when x equals 1, it represents, okay, your outcome is head. If x equals to 0 means that your tossing ends up with the tail. Right? If we toss the coin for 5 times, right, that's the experiment we just have done, right? So we can introduce 5 random variables, x1, x2 to x5, right? Now we want to represent a particular event that we have less than 3 heads in terms of these 5 random variables. How can we do that? We can use an equality to represent such event. Namely, the summation from x1 to x5 is less than or equal to 3. Right? Then the probability of the probability that this event, namely we have less than 3 heads happen, is the probability that this inequality holds. So this is the definition of random variables and how it is associated with random events representation. Right? So for any random experiments, we can either use sets to represent all kinds of original events, or we can map them into some numerical numbers, which are called random variables. Right? And the events are turned into some inequalities. So based on random variables and random events definition, we can define the joint probability of several random variables or several events, right? So suppose I have events A and B. We can define the joint probability of A and B as the probability A and B both happen. So this is actually the probability of A intersection of A and B, right? So it's not union A and B. Be careful at this point. Right? So the joint probability of A and B is equal to the probability of A multiplying with the conditional probability that B happens given A happens. And symmetrically, it also equal to probability of B happens multiplying with the conditional probability of A happens given B happens. If we want to measure the probability in terms of random variables, and random variables continuous, then we call it joint probability density. P of x and y. So P of x, y has very similar decomposition as P of A and B, right? So this is equal to the marginal probability of x multiplying with the conditional probability of y given x, and also equals to a probability of y multiplying the conditional probability of x given y. Everybody's comfortable? Right? We just walk through some concepts we have learned maybe years ago, right? So now, given the joint definition of joint probability, we can introduce the concept of independency, right? So intuitively speaking, like independency means that okay, the occurrence of two events are independent of each other, have nothing to do with each other. Like if I say okay, random events A and B are independent to each other means that okay, the occurrence of A has nothing to do with the occurrence of B, right? But in math language, how do we define independency? As long as the joint probability of A and B equals to the product of their marginal probability respectively, then we claim that A and B are independent of each other. And similarly, if you want to claim two random variables, x and y, are independent, we just need to show that the joint probability of x, y is equal to the marginal probability of x multiplying the marginal probability of y. So now from this definition, we can also use another definition of the independence. How can we do that? We can take a look at the original definition, joint probability, and the condition for independency, right? So you can see that independency simply means that the marginal probability equals to the conditional probability. Right? So it means that, okay, if A and B are independent, it means that the probability of B is exactly the same as the probability of A given B. Oh, sorry, the probability, I should say, the probability of B is equal to the conditional probability of B given A. Or in other words, you can contrast this term P of A and P of A given B. Right? So if A and B are independent of each other, it simply means that the marginal probability of A is equal to the conditional probability that A happens given B happens. So intuitively, it explains why it is independent. It means, okay, no matter B happens or not, it doesn't affect the chance that A happens. Right? And similarly, to test whether two random variables x, y are independent, we just need to test whether the conditional density is the same as the marginal density, right? Whether P of x is equal to P of x given y, right? Or whether P of y is the same as P of y given x.
So if x is dependent or independent of y, then y has to be independent of x also, right?
Yeah. So this is actually means it's a mutual concept. If I say okay, x is independent of y, it means that y is independent of x. So we can further extend the concept of independency to a conditional independency. Right? We see that two random events A and B are conditionally independent given the third event C if the conditional joint probability, namely P of A and B given C, equals to the product of the conditional probability of A given C and the conditional probability of B given C. So you can see from the form, you can see it's quite simple. Just put a conditional notations on each term. Similarly, for if we want to verify whether two random variables x, y are conditionally independent given a third random variable z, we just test whether their joint conditional probability given z is equal to the product of p of x given z multiplying and p of y given z. Any question at this point?
So if two variables are independent, are they also conditional independent?
No, it's not. There's no guarantee on that. Any other question? So this is kind of subtle. But be aware, like conditional independence is different, totally different from marginal independence. Okay. So given random variables, we're interested in a few important statistics regarding these random variables. Right? For example, the most important properties or statistic regarding random variable is expectation. So what is expectation? It is essentially the average of the values of random variable weighted by its probability densities. So the definition of expectation is an integral, where the integrand is x itself multiplying with its probability. So if x is discrete, p of x is discrete as well. You can see this is actual weighted average, right? But if x is continuous, p of x is continuous, this is actually an integral. So conceptually, they're the same. It's just a weighted average. And we can extend this concept to the expectation of a function of random variables. Right? So suppose I apply some function g over the random variable x, how can I compute the expectation of gx? Same thing, right? In an integral, we just replace x by g of x. So in addition to expectation, which is the average value of the random variables, we're also interested in variance. Right? So what does variance indicate? So again, imagine a random variable, right? It is not some fixed constant. Right? As a chance will appear here, a chance appears here, a chance appears here, right? Now we know on average it will stay in the middle, right? But we would like also to know on average how the random variable jumps away from its expectation, right? That's what variance tells us, right? So definition of variance is as follows. So it's an expectation of the square of the random variables subtracted by the square of the expectations. But this is for scalar. This is for scalar. If our random variable is a vector, so it's called random vector, and usually we're going to compute the covariance matrix. Say if x is a m-dimensional vector, the covariance matrix will be m by m, right? So each element of the covariance matrix just means the covariance, in other words, correlation between two elements in this random vector. And the definition is as follows. We're going to compute the expectation of x transpose. So the outer product of this vector. So it will be matrix, right? Subtracted by the outer product of its expectation vector. So this is just definition. And similarly, we can define conditional expectation and conditional variance, right? So how can we compute conditional expectation? How can we compute conditional expectation? We just replace the probability density here by the conditional density, right? So if I want to compute the conditional expectation of x given y, then in the integral, I'm gonna replace p of x by p of x given y, right? And then similarly, you do the variances here, right? So the expectation of x squared given y and expectation of x given y squared, right? So now I want you to be aware of the subtle things here, right? So I want to ask, is a conditional expectation a constant? Does the conditional expectation have some randomness? I see someone nods, right? Can someone give me an explanation or give me a hint?
Why?
Yes. Why?
By definition of expectation of x, y in at the point y.
So if we look at this definition, right, just as you suggested, right. So if we replace p of x by p of x given y, we integrate out x, right, and then the conditional expectation will be a function of y. Remember, y is a random variable, right? So the function of a random variable is another random variable. So the conditional expectation must be a random variable. Similarly, the variance is computed from the expectation. So the variance, the conditional variance must be a random variable as well. So that means it can vary along the value of y. So in our home of 0, you're required to prove some classical theory. That is, the expectation of the conditional expectation is the expectation of x. Please try to do that. This is a very good practice to deepen your understanding of the concepts of expectation variance. So now let us introduce another important concept regarding functions, that is convex functions. The first convex functions are defined on convex region or convex set. So that means the domain of a convex function must be convex. So what does convex set mean? Convex set is a set of numbers such that if you connect any 2 points in a set, the segment between x and y must all belong to the convex set. That means any combination of x, y, which in between x and y must stay inside the set. That's the definition of convex set. So this is a convex set because if you pick up any 2 points, you connect them, the whole segment stay in the set. But this one is not a convex set. Why? Because if we pick up x here, pick up y here, right? If you connect them, you see this red part is going outside of this set, right? This is not a convex set. So intuitively, very roughly speaking, convex set visually must be outward, right? It cannot be inward. If it's like inwards like this, right, you can always find some 2 points, you connect them, and some partial segments will be outside the convex set, right? It won't be convex set, right? So convex function is a function defined on convex set such that any 2 points in your input domain and arbitrary coefficient between 0 and 1, the function value evaluated at the linear combination of x1 and x2 by the coefficient t is less than or equal to the linear combination of the function values at x1 and x2 weighted by t. Right? This is the core requirement of the convex function. This equality must always hold. Right? So we have some visualization of this inequality. So this function is a typical convex function, right? If we pick up actually two inputs in the domain, right, which is x-axis, say x1, x2, and pick up a coefficient between 0 and 1, t, right? So then tx1 plus 1 minus tx2, the combination of x1 and x2, must stay in between x1 and x2, right? And then the function evaluated at this combination of x1 and x2 is here. You see? And the linear combination of the function values at x1 and x2 weighted by t can also be drawn here, right? So we can say the function value x1 is here. The function value at x2 is here, right? If you want to know their combination weighted by t, we just draw another line and draw lines vertical to the y-axis. Here is the weighted combination of the function values at x1 and x2, right? This is the right-hand side of this inequality. So right-hand side of this inequality is here. So you can say, obviously, the function value at the combination of the inputs is less than or equal to the combination of the function values. You can choose arbitrary 2 points for this function. You can always find this result. So any question regarding this definition? Or everyone is familiar with this? Is everyone comfortable with this?
So you're just saying all the y points on the diagonal line that connects the two are bigger than all the y points below it, right?
On the curve, yes, exactly.
The curve is flipped upside down, would it still be convex?
You mean going this way and going this way?
So the curve is like a...
No, it's not convex. It's all concave.
Okay.
If you define a function to satisfy inequality that with reverse direction, that means you change this less than equal to be bigger than equal to. This is called concave function. Any question?
Can we say that if the second derivative of the function is positive, it's always convex?
Yes. That's a very commonly used criterion to test whether your function is convex or not. Second order derivative, whether it is positive. Yeah, I'll list it later. So here's a set of examples of convex functions. Like for a single variable, exponential function is convex function. And where log of x is not convex, it's concave. Minus log is convex. And here is some like vector functions. X can be vector. And remember, x can be vector because this inequality does not restrict the x1 and x2 must be scalar. It can be vector. So this function is called linear function. Sometimes it's referred to f functions, always convex. And quadratic function is convex.
The second example that you gave for single variable, so is the base important? I mean, for minus log x, is the base for log x?
It has nothing to do with base.
Any log
will be convex. Other question? Okay, so things come to like how we determine a function is convex or not, right? So obviously we can use the definition to do that, but in many cases it's not very easy to show the utility holds, right? So here are the two very commonly used conditions to test whether a function is convex or not, right? So if your function is differentiable, then if you can show that for arbitrary 2 inputs x and y in your domain, f(x) is always bigger than or equal to fy plus the inner product between the gradient of function at y and the difference between x, y. Then we can conclude that f is convex. So the right hand side is essentially a first order Taylor expansion, right? First order Taylor approximation of your function. geometrically speaking, is a tangent line at position y. So basically, the geometric meaning simply says, okay, the convex function must stay above any tangent line. Right? If you go back, so the right-hand side is fy plus the inner product between the gradient and x subtracted by y, right? Is actually a tangent line. A tangent line cross the particular input y, right? So it requires that for any x must be bigger, fx must be bigger than this line. Just means, okay, the whole curve must stay above its tangent line. This is a very famous geometric view of convex functions. If you're interested in, please open any convex functions and try to draw those curves ourselves. And another important or commonly used condition is to test the hash matrix, namely second order derivative. If fx is x is scalar, then second order derivative is scalar, and if it is always bigger than or equal to 0, fx is convex. If x is vector, then second order derivative will be a Hessian matrix, right? The Hessian matrix, as long as it's semi-positive definite, then the function is convex. So actually, you can use the two conditions to solve problem 7 or 8 in homework 0. If I'm not wrong, I forgot the problem number. And another very important inequality associated with convex function is called Jensen's inequality. So what is Jensen's inequality? It basically says that if x is a random variable and f is convex function, then the function value at the expectation of x is less than or equal to the expectation of the function. Right? Remember x is a random variable, right? So f of x must be a random variable as well. So we can take expectation of fx. So convex function means that, okay, when I evaluate my function at the expectation of the random input, it should be less than or equal to I take the expectation of the function of the x. And this can be extended to some function of random variable as well, right? You can first do some function of x, gx, and then you can still apply Jensen equality. Any questions so far? Okay, great. So, and final piece of things I want to mention is the matrix derivative. Right? So actually, if you really want to do research in machine learning, our basic elements in machine learning is matrix and vectors. We rarely describe how do we deal with scalars. Everything you assume is matrix, vectors, sometimes tensors. That means you have to be familiar with the matrix, vector, all kinds of linear algebra operations, and also many objective functions, maybe loss functions or maximum likelihood, are represented in terms of matrix and vectors. And during the learning, it's essentially in many cases correspond to some optimization procedure. That means we have to maximize objective function, minimize loss function in terms of matrix vectors. So you need to know how to calculate the gradients with respect to matrix vectors and vector variables. But this is not. This is actually a quiet mechanic. What you do is that you just follow the chain rules. The chain rule is very similar to scalar gradient computation, and then you reach at these basic situations, which we call atomic situations. Like the derivative of some constant matrix is 0. Of course, it's 0 matrix, right? And derivative of some constant alpha multiplying with our matrix variable x is alpha times the derivative of x, right? So the derivative of addition of two matrix variables is the addition of the derivatives of each matrix variables, right? So there are some interesting conclusion regarding matrix derivatives, like derivative of trace of x is equal to trace of derivative of x, right? Derivative of x and y equals to derivative of x multiplied with y, x multiplied with derivative of y, right? It's the same as scalar, right? And regarding and also the derivative of x, element y is product with y, Kronecker product with I, inverse of x, determinant of x, log determinant of x. You don't need to know how those kind of things are derived. They have been proved and summarized by pioneers. All you need to know is know those basic rules and then just expand everything in terms of chain rule, right? So there is a very good reference book called Matrix Cookbook. It records all kinds of like such kind of basic situations. I just list the most common used ones, but that book is kind of a wiki book. So the routine is that you just apply chain rules. When you find something, some derivatives you feel is element, you just look up the matrix cookbook and find a result and copy the formula. That's how we do that matrix derivative. So hopefully you can utilize this matrix cookbook to solve the last problem or the second last problem homework here. Okay, any questions so far regarding the basic concepts and knowledge review? If everyone is comfortable, we're going to start our function. So, oops. So in the remaining time for our lecture, we're going to introduce the general framework of supervised learning. As we mentioned in our previous lectures, supervised learning will be our focus of this machine learning class, right? And then we'll introduce representation of decision trees. Decision trees will be our first supervised machine learning model to discuss. So this is the outline, right? So first, what is the general setting of supervised learning? And second, some warm-up about decision trees. We start with the representation of decision trees. Okay. So first, what is supervised learning? So we very roughly introduced supervised learning at the beginning of our class, right? We mentioned that supervised learning is just like teaching you how to solve problems, right? I give you a set of problems and their answers, and from looking at those examples, which we refer to as training examples, you learn how to solve problems. They can present, when I give you a new problem, you can use technique to solve it, right? In practice, when we conduct supervised learning, we need to first figure out what are the instances and what are the labels. Let us look at some concrete example. Suppose our task is to develop some programming smart program to automatically tag news articles. Suppose I have a news article. I want to assign a label on that. Say, I want to assign a sports label on that. Basically means I classify this piece of news article I'm talking about sports, like baseballs or football, whatever, right? So obviously, we can collect all possible news articles. We refer them as instance space. So basically, instance space means that all kinds of articles that I need my program to tag or classify, right? And similarly, I need to identify all possible labels I could give those articles, right? News articles, right? So those tags could be sports, could be business, could be politics, could be entertainment, could be financial, whatever, right? But anyway, before we conduct this supervised learning task, we must know, okay, what specific set of labels I'm going to tag the news articles, right? Also, I want to know the range of the news articles that my program would like to tag, right? So those actually lead to the general concepts in machine learning, in supervised machine learning. The first is called instance space. So basically, we need to define what is our instance space. Namely, the set of examples that need to be classified in our supervised learning task. We also need to define the label space. Namely, what kind of the set of all possible labels those instances could have. Right? And usually, if we conduct supervised learning, we believe there is some ground truth target function which map the instance in the instance space to the label in the label space. I know there's some like a powerful classifier which can correctly classify each tag of the news article. Right? And the task of our supervised learning is to find out this target function, or in many cases, find out a good approximation of this target function. And the learning procedure is essentially a search procedure over the functions. So basically, in many supervised learning algorithm, I'm gonna like indicate the family of candidate functions. Then just search over this candidate function family and find out the one which I believe it is closest to target function, or it is target function. But how can we conduct learning algorithm, right? So obviously we do not know the target function, right? What we have is just a few examples of the instances and their labels. So based on those examples, we want to find out the target function or the close approximation of this function, right? So those examples we call them training data. Abstractively, we can view them as pairs of the instances and their labels, right? So suppose we have like n training examples, we represent as x1 fx1, which is the ground truth label, right? x2 fx2 until xn fxn, right? And this actually form the input of our supervised learning algorithm. Right? We feed this labeled training data to our learning algorithm, then we expect that the algorithm will return a learned function g, which is also mapping from the instance space to the label space. So this is the setting of the supervised training. And it's also the protocol of the learning procedure. You prepare a set of labeled training set, you feed them to our learning algorithm. Our learning algorithm will return you a learned function, which is essentially a mapping. Right? But obviously, we can change this protocol a little bit, right? Then it corresponds to another branch of machine learning. So what if I do not provide labels? What if I want to develop another type of learning algorithm such that my input is just a set of unlabeled training examples, unlabeled instances, right? Can I still output a learned function which maps the instance in the instance space to the labels in the label space? This is called unsupervised learning. And sometimes we can even prepare a mix of labeled and unlabeled training examples. Say part of them are labeled, and part of them do not have any labels. Then we'll feed them into a learning algorithm. We still want the learning algorithm generate a function. This is called semi-supervised learning. So you see, different branches of machine learning just correspond to different learning protocols. But as we mentioned before, supervised learning is the most important. Once you are familiar with supervised learning, you say, okay, unsupervised learning, semi-supervised learning is just a kind of extension, natural extension of the supervised learning. Any questions regarding the definition of the general settings? Okay. So everybody is coming.
So just kind of go back to your example of like how you learn with like the, given a set of information and a set of answers. The labels is essentially like the answers that you're giving to it, so
yes,
it understands.
Yes. Yeah. Correct. Yeah. And yeah.
On the neural algorithms, when you take a picture, it can group like who's in which photo by the faces that's in it. Would that be an example like unsupervised learning, since you're not talking like, okay, this person's in this photo, it's kind of just grouping them?
Yeah. Actually, as you mentioned, right? If you group the images into like different people's photos, right? So those groups indicate the labels. So unsupervised learning usually does not have like an explicit label space. You need to also find the potential labels of the training samples. Your question?
I was going to ask, if we do not have the training data for the unsupervised learning, I mean, we do not have the labels. How can we find the labels?
As he just mentioned, right? A most common method is called clustering. You're grouping your training instances into different clusters, right? Even each cluster actually represents a particular type of label. Like if I present you a set of documents, or a set of articles, right? You group them into different topics. Although you might not know the semantic meaning of those group of articles, right? But when you read it, you might, okay, group 1 generally talk about politics, right? Donald Trump or whatever. And group 2 talk about Brad Pitt, divorce with Angelina Jolie, or third topic you may talk about like what? Huh?
So unlabeled training data, unsupervised learning, is a lot like letting the system come up with its own labels.
Yes. Yes, exactly. And usually, you do not need to specify what kind of labels, what kind of tags you're gonna give. Sometimes, in most cases, you even do not know. It's kind of discovery. I don't know which of you.
Okay.
Who of you? Yep. Okay.
Just not to belabor the point, but just to get a little more clarity. So, supervised learning would say your training data is just like a bunch of articles, and you specify the labels are business, sports, and entertainment. And unsupervised learning is you have a stack of articles, and based on like keywords or some data, the function determines the labels.
Yes.
Yes.
Yes, exactly.
I mean, you mentioned that in unsupervised learning, you potentially don't know how exactly what the label is, right? So
Yes.
how do you actually kind of validate saying that okay, this is a good classifier in the term, because you don't even know actually.
Yeah, that's a very good question. Actually, this is a problem of the unsupervised learning. Actually, the community, I mean, the researchers in unsupervised learning haven't yet come out a very convincing metric to justify your unsupervised classifier learner is very good. So although there are many metrics like clustering purity, like perplexity, or many interests. It just says, okay, if your cluster is very pure in terms of what, but if you evaluate, you might need like third-party labels on that, or you might need human reviews, right? If you look at, like human beings to look at whether they essentially reflect some particular type or labels on that. But to automatically do that, there are always some kind of defects on those evaluations. Other questions? Okay, great. Yeah. So now kind of problem, right? So if we have developed our supervised learning algorithm, our algorithm is executed with some training data as input. We have obtained our learn function g, right? The next question would be, how do we evaluate whether our learn function g is good or not, right? Whether can we justify or can we claim our learning is a success, right? So ideally, we would like to directly compare the target function with our learn function. If they are the same, or g is close to f, then we win, right? But this is just the ideal situation. Because if we know the ground truth, why do we bother to train some machine learning algorithm on that, right? Directly use it. Therefore, in practice, our evaluation follows another way. We draw test examples from our instance space, and then just look at the prediction of the target function and our learn function, and see whether they are the same. Right? If you draw like 10,000 examples and 999 examples are the same, have the same prediction from our learn function with the target function, well, you can safely claim that your learn function is very good, right? Otherwise, you might have a problem on that. So this is the general strategy we choose to evaluate our learn function. Right? But here I want to ask you a question. And usually to ensure that our test is reliable, we have to draw many test examples. If you just 10 examples as a test, that's not very reliable. But here I want to ask you a question, right? Can you use test examples during the training?
No, because that's what you would verify with, right? So
Yeah.
you're using a training set to train your target function, and the test examples would be what you would test.
Yes, you're right. So this is a very important principle. Never ever use a test example during the training. This is called cheating. So actually, you can imagine that if I use test examples for training, right? I do not need to write down any to develop any algorithm. I just memorize all the test examples. Then my test accuracy always be 100% accurate, right? But can we conclude that our so-called learning algorithm perform very good? No, right? So actually, this is a very common mistake made by machine learning researchers. I mean, even very experienced researchers, right? So if you find that your machine learning algorithms produce surprisingly good results, don't celebrate. Don't celebrate. First, check whether you overlap your test example with training examples. This is a very important rule.
About like things that are super similar, so like yeah, it's like the code fix is different or something like that, and classified as cheating or you know what I mean?
Yeah, and I know. No, it's not called cheating. Cheating is just you use the exact test examples for training. If your test example is a little bit different from training, it's fine. It's totally fine. Any other question?
So, I mean, for any such situation or a problem that we're trying to approach, we have a set of known solutions, right? Something like a set of known labels, a few of them will be known. So, how do you kind of like split the total known labels, I mean, the instance and label kind of pairs, right? So, how do you split them into a good test set and a good training set? Like what ratio do you put for that?
Very good question. This regarding like how do you test the general performance of the model, right? So our labeled training example is always limited, right? So a common use strategy is to do cross-validation. You have to randomly split your label, the whole label data set, into training set and test set many times. And for each split, you train a model, you test on the test set, you get some accuracy, right? And do it again and again to increase the robustness of your measurement. Right? And finally, on average, if your performance is very good, then we can claim that your performance is good. We'll talk about it later.
In the class, we're going to like cover strategies for when you don't have that much data, so you can't really like do large splits of test and training data. Maybe only like 20 observations or 30 observations.
In that case, you shouldn't do machine learning. Machine learning is kind of data-driven process. The precondition that you have sufficient data. I do not mean to like have billions of examples, but if you only have 10 examples, it's not necessary to do machine learning. You have to have like sufficient examples. Like a few hundreds could be fine, right? But if it's too few, then all your results, all learning results, are not reliable at all. Does it make sense?
Yeah, is there like a deterministic formula of like what the minimum sample size would need to be for like different types of models?
Oh yeah, that's a very good question. That's regarding the theoretical guarantees about machine learning. Right? We'll cover a little bit on that, like how can we characterize the generalization performance, namely the prediction accuracy varies along with the number of the training samples. So intuitively, we expect that the more the training examples you have, the more accurate your learned classifiers or predictors will be, right? But it depends on how you. It also depends on how you design your machine learning algorithms. What type of classifiers you choose.
How does the outliers in our test or training set basically affects the robustness of the learning?
It depends. It also depends on what specific machine learning model you choose, right? And actually, if you choose very complicated models like artificial neural nets, then you can well fit all kinds of training examples, even including outliers. But it might bring in severe problems called overfitting. So overfitting is not a good sign in machine learning world. It usually indicates worse generalization performance. But if you choose very simple model, you might underfit data. That means you cannot fit the outliers, but at the same time you won't be severely affected by outliers. This is a kind of a trade-off between this overfitting and underfitting, and we'll discuss in detail data as well. Any other questions? Okay, great. I think you guys asked a lot of insightful questions. I didn't expect it. Okay. So now let us talk about the general settings of the supervised learning. So first, just precondition. We need to prepare a set of training examples in the form of the instance and label pairs, right? And the function f is an unknown function. And typically, the input x is represented in a feature space, namely vectors. So for example, your input x could be like undimensional binary feature vector or undimensional continuous feature vector, right? So usually from the original instances, you need to extract a representation of those input x, which we call a feature extraction. This is a very important procedure. So why can't we directly use the original instances? The reason is that this is machine learning, right? We write down a program, computer program. Computer program can only handle numerical values. You cannot directly throw a piece of paper in front of a computer that it to do whatever, right? You cannot directly throw out a photo, right? You need first extract some numerical representation of your photos or of your articles, whatever, right? So this procedure is called feature extraction. So feature extraction, although is not inside the supervised learning algorithm procedure, but it's very, very important pre-processing step. So many learning tasks, whether it succeed or not, depends on whether you have successfully do the feature extraction. And then given the training data set, our supervised learning aims to find a good approximation of our target function f. And the label, in the label space, actually determines the type of the supervised learning problem. If your label space just contains two labels, like -1, +1, then this task is called binary classification. If your label space consists of like finite discrete labels, this is called a multi-class classification. If your label space are continuous, say a real domain, right? Then this task is called regression. Any question?
Sorry, is it feature extraction? Is that unique to supervised learning? Like you wouldn't do something like that in unsupervised learning?
No, actually, feature extraction is the pre-processing step for all kinds of machine learning problems. The reason is that you have to represent the instances in a way that the computer program can process, right? The computer program can only process vectors of numerical values, right? Binary or real values, whatever, right? So if your original instances are not numerical values, you have to convert them into numerical representations. But how do you well represent your original instances by numerical vectors? This is an important procedure. It's a non-trivial procedure. It's not that easy. Because actually, in machine learning practice, when you do the course project, you might have a few on that. Different ways to do the feature extraction will lead to totally different performance, even if you use exactly the same learning model and algorithm. Okay? Any other questions? Okay. So when we conduct supervised learning, please be aware of the following questions, because we need to answer those questions before you start to do it. First, you need to answer what is our instance space. It's actually specify the range of the instances you want to classify or you want to predict, right? And also, what are the features? This is regarding the feature extraction procedure. How can I extract some numerical features to well represent or to comprehensively represent the original instances, right? Say if you presented the computer program a photograph, not a photograph, it's just an image, right? How do you represent? You just vectorize all the pixels on that, or you just sample a few of them, or just do the average blockwise on the images. There are many ways to do that. Right? And given the instance space, you need to consider what is our label space, right? It actually defines the specific task, right? If you want to just classify your emails to be a spam email, to be a normal email, then it's just a binary classification problem, right? Your label space only contains 2 labels. If you want to predict the stock price, then it is a regression problem. The label space will be filled with all kinds of the continuous values. And then you also need to define a hypothesis space. Right? This is a new concept. What is hypothesis space? Hypothesis space essentially is the family of the candidate functions your learning algorithm will search over. As we just mentioned, learning procedure is essentially a search process, right? You're going to find out some function which you believe is close enough to the target function. Right? But before you do the searching, you need to know the range of the search. Right? So a hypothesis space is the range of search. There's also the definition of hypothesis space also defines or determines the complexity of your machine learning models. Right? For example, if you can define, okay, my hypothesis space is just all the linear functions. It could be simple, but it might not be expressive enough. Someone may ask, okay, I want my hypothesis space to be very large, include all kinds of linear nonlinear functions like artificial neural nets. But that will bring in another issues. That means if the model is too flexible, it can fit all kinds of data. It might bring in overfitting. Overfitting is not good. It's not a good machine learning. We will mention the trade-off to select hypothesis space. And then, given the hypothesis space, you need to choose particular learning algorithm, right? Do you want to do the just the combinatorial search or to do the gradient-based search? Which one is better? It depends on the application, right? And finally, after you have developed an algorithm, and after you run an algorithm and get some classifier, you want to evaluate whether a classifier is good or not, right? Then we need to come out with the evaluation metric, right? Sometimes the evaluation metric is reflected in so-called loss functions. We're going to use this evaluation metric to test whether our learning is successful or completely failed. Right? So those are 5 key problems whenever you conduct a supervised learning task. Right? Explicitly or implicitly, practice, you have to address those problems when you do a supervised learning task. So here is the brief taxonomy of supervised learning, unsupervised learning, and semi-supervised learning. If you take a look at this, quite similar to our course content organization. Right? So supervised learning, the most intuitive supervised learning, I believe, is our decision trees, which is the first algorithm models we're going to discuss. And boosting and ensemble learning is a collection of decision trees. How do we combine them to be more powerful. And then we can classify supervised learning models into basically linear models and nonlinear models. So this is classified according to the hypothesis space, as I just mentioned. Right? If I choose linear functions or linear structural functions as the hypothesis space, we call them we generally call them linear models. Those include like linear regression, logistic regression, line-based perception, support vector machines, and etc. If you use nonlinear candidate functions as a hypothesis space, we refer them to as nonlinear models. There's a very simple model, but very powerful machine learning model is called nearest neighbor classifier. It's a nonlinear model. Polynomial regression, kernel methods, the kernel version of support vector machines, kernel perception, kernel regression, etc., and artificial neural nets. Very typical nonlinear supervised learning algorithms. Right? And unsupervised learning, like clustering and dimension reduction, etc., and semi-supervised learning. Right? So we're gonna start with decision trees. So this is the plan for us to discuss the decision trees. So first introduce the representation of decision trees. What's the definition of decision trees, right? And then we'll introduce the learning algorithm of decision trees, namely how can we automatically construct decision trees out from training data. We'll cover the classical ID3 algorithm, which is essentially a greedy algorithm. And then on top of that, we'll introduce a few variants of ID3 and a few extensions to further improve your performance, like post-browning to avoid overfitting and other node splitting principles. The original ID3 use information gain to split the node, but sometimes you can change to a more robust, in other contexts to be more robust other principles, right? So why do we care about decision trees? The first and very important reason, it is simple and intuitive. As we will say in a minute, you'll see that decision trees are essentially a set of rules, right? It's very similar to human beings' decision procedure, right? We always come up with a set of rules to make our decision. And secondly, decision trees has very good interpretability. It's not like 100-layer deep neural nets. You don't know. You can only treat it as a black box, right? Decision trees is completely transparent. You can analyze why it comes as a path from root to leaf and why the roots look like that. What is is it make sense or not, right? And third is that don't look down upon decision trees. Although it has been invented for 30 years, but it's very widely used and can be further promoted to be very, very strong. This is called ensemble learning, like boosting random forest, breeding boosting trees. They are kind of they're kind of like the standard, the first choice in many applications. Decision trees are very widely used. So now let us first look at representation issue. What are decision trees, right? So I will first give a general description about decision trees, and then we'll look at some concrete examples. Right? So in general, the decision tree is a hierarchical structure that represents the data with a divide and conquer strategy. So it must associate with the tree structure, right? And each node in the tree actually represents a data subset. And meanwhile, each node is associated with some test feature. So it uses feature to split data set recursively until it reaches the leaves. From each node, one branch is created for every value that the test feature can take. So if I associate with node with a particular feature, if the feature can take 3 values, it naturally split the data set into 3 subsets, right? And then we have 3 new nodes represent 3 subsets, and for each subset, we're gonna create new branches based on another feature and do it partition until we reach the leaves of the tree. So the leaves of the tree specify the class labels. Those are also the point where we stop partition the data. And the general idea of decision tree learning is to construct a decision tree represent the given collection of the labeled tree data. So now let us look at a concrete example, right? So this is our training data. This is just a set of ships, right? And I want to construct a decision tree to represent those training sets. So first we observe that there are 3 labels, right? 3 possible labels, A and B and C, right? We have 3 types of labels. And before we build a decision tree, can anybody tell me what is label for a red triangle? Red triangle does not appear in the training set. But now, if I give you a red triangle, can you tell me which label you're willing to assign?
B.
Why B?
Because it's the only label that has a color.
That's where all the reds are, and that's where all the triangles are.
Yes, right? It's very intuitive, right? Because, okay, no matter what kind of ships those instances have, right? We know, okay, as long as red looks like it just have the label B, right? So naturally we want to assign a red triangle to have label B as well, right? Now let us keep this question in our mind, right? We need to construct the decision tree, as we know, right? We split the data according to features or attributes. So what attributes do we have for those examples?
Shape, color.
Yeah, shape and color, right? So we have like circles, we have rectangles, we have like triangles. We also have green, blue, and red, right? So now let us try to use these 2 attributes to construct the decision tree, right? So let us start with color, right? So what possible colors do we have? We just mentioned 3 possible colors, right? So blue, red, and green. That means according to different color values, we can partition the whole training set into 3 piles, right? So for the subset of instances which have red colors, we know those 3 shapes all have the same label, B. So stop here. Because all the instances have unique label, right? It's not necessary to split them. And next, let us look at the blue shapes and the green shapes, right? So for blue shapes, all the blue shapes actually have like 3 labels, right? A and B and C. So of course we can also stop, and we need to continue to partition the blue shapes according to their shape attributes, right? So we have 3 possible shapes: triangle, square, and circle, right? So for the blue shapes, for the blue instances, if the shape is circle, we know all those blue circles have the same label C, right? So we reach the leaf and assign label to be C. And for blue instances which has the shape square, which label do we have? A, right? There's only one instance. This blue square only has label A, so stop here and assign label on the leaf, right? And finally, for the blue triangles, we say, okay, all the 2 blue triangles share the same label, which is B, so stop here. Right? And similarly, we can partition the green instances according to their shapes as well, right? So we found that all the green instances only have 2 shapes, circle or square, right? If the green instances are circles, they have the same label A, so stop here and assign a label A as a leaf, right? And if the green instances are squares, they have the unique label B, so stop here. So now we finish the construction of our decision tree. So say each node in the tree actually represents a subset of data, right? The root represents the whole data set, right? And then you go through each subset and you partition them according to different feature values. So now suppose I have this tree in my hand, right? How do I use this tree to classify the labels for new instances, right? How can we do that? We just follow paths from the root to leaf according to the attributes of the instance, right? For example, if you want to predict the label for red triangle, as we just mentioned, right? We first look at the color of red triangle. Okay, it's color, right? Do we need to further test? No, because it stops here and leaves. We give the label B. So it's consistent with our intuition, right? But here is another question, right? So now, if I give you a green triangle, can you predict its label based on this symmetry?
No.
No. Why?
It never gets to a leaf.
Yes. Because we cannot find a leaf. I mean, by following the path, right? There's no path from the root to reach the leaf to give you a label for this green triangle. The key problem is that because when we partition the green shapes, right, there are only like squares and circles. There's no triangles, so it doesn't have a leaf on them. This is actually not acceptable. It's very embarrassing if you construct a classifier. You will throw a specific example, it refuses to give you an answer. It's not acceptable. So when we develop our own algorithm to construct decision tree, must fix this issue. As to how to fix that, we'll discuss later when we talk about ID3. Right? This is very important, detail we need to address. So, what decision functions do decision trees represent? As we mentioned, right, there are essential rules, right? So each path from the root to leaves indicate one specific decision rule to do the classification. So decision tree essentially, the full tree is essentially a conjunction of all the rules. So you can alternatively represent decision trees as a conjunction of set of rules, which enumerate all the possible passes from the root to leaves. So this is also some compact representation of decision trees. Okay, I think we can stop here today, right? So tomorrow we'll finish the remaining properties of decision trees, and we'll look into the ID3 algorithm to automatically learn decision tree from data.
In that example, the features were both like that. What if they were like a real number? Does it just decide some sort of arbitrary like points?
Yes, you're right.